Hello. In this talk, we're going to review what we have learned over the last few weeks, specifically over psychrometrics. We have three objectives. Number one is to review what we have learned, primarily the concepts and those variables associated with those concepts. And second is to see how those concepts are applied in the air conditioning design. And then we will see how we can solve some engineering problems. The concept, actually, we have learned three major things. One is sensible heat, the other latent heat, and then the other thing is what we are already familiar with is energy conservation. Energy transfer from one form into another. For example, in the first week, we look at how electricity, energy in electricity turn into water in heat in the water. And then we also see how the electricity energy turn water into vapor. So if the energy stored in the water as temperature raise, this is called sensible heat. And if the energy turn water into steam, this is latent heat. And then the heat doesn't disappear anywhere or does not appear anywhere. It always transfers from one to another. And this also associates with the heat exchanges. We will see this later. So associated with the heat, sensible heat, we have a specific heat. And we did the experiment to find out the specific heat of water. And then we didn't do air, but I tell you that air specific heat is equally important as the water specific heat. And we also introduce another parameter, is heat of evaporation. And heat evaporation is the same concept as specific heat. So we need to find out, we need to be very clear how these two are defined. What do they mean? For instance, specific heat is the energy needed to raise 1 degree for 1 kilogram of material. And the same, the heat of evaporation is the energy needed to turn 1 kilogram water into vapor. Okay, so if you have understanding how these two variables are defined, you'll be able to write the formulae, the two formulas. Right, based on these three concepts, we looked at 7 psychrometric properties of the air. Right, we start from water and we go into air. We consider air is a mixture of vapor and air, dry air. So therefore, we need 2 variables to define the state of the air. So very common, the most common way is to provide dry bulb, wide bulb temperatures. So we have 2. So these 2 are easily measured by sling thermometers. Then second is percentage of saturation. This is defined how much moisture contained in a piece of air and how close to the saturation. If it's 100%, that means it's saturated. You cannot add any more vapor into the air. If you keep adding the moisture into the air, you will see it turn into steam, mist, or dews somewhere in the air. Now, the other one is relative humidity. That is, again, percentage, very similar to the saturation. They have the same value, although they have different definition. We do not care how they are defined. But anyway, they are just 2 measures to show how much moisture in the air, how close to the saturation. Now, the fourth one is dew point. Dew point is the temperature at which we start to see the dew or mist. Vapor is not visible, but if the temperature keeps dropping to a point, we start to see the mist. This is a point we call dew point. Or if we look at the temperature at the surface, and then the temperature of the surface drops to a point, we start to see it become wet. You can see the dew appears on the surface. This is the point we call dew point. Then specific volume is per kilogram of the air, the volume of the air. And then the specific enthalpy is the energy contained in 1 kilogram air. And that air is a mixture of dry and vapor. So therefore, it has sensible heat for the mixture air and vapor, and also latent heat. So it has co-components. So these are the concepts, and associated with 3 major concepts, we have 7 variables, right? 7 variables, and the 2 specific properties for the air. Now, application, we see how the heat transfer from water into air, or from electricity into the air. Okay, and also you can see in the cooling coil how the heat being taken away at the coil by refrigerant or chilled water. Okay, so this is kind of coil. So a coil is a device allow 2 flows to contact each other. Therefore, we introduce another variable to define this kind of contact. If there's a 100% is 1, contact factor is 1, that means this have been a perfect contact. Now, if there's a very small contact, the value would be smaller, close to 0. So this is a physical measure, it's a description of a physical feature for the 2 flows to contact each other. And then we have another engineering. So the cooling coil, heating coil is engineering solution allow heat exchange to take place. And similarly in engineering, we tend to mix 2 different flows together, and then we have a new temperature or new moisture content or new specific volume, a specific enthalpy, and so on and so forth. So when we mix 2 different air flows, and then we have a new state of air, and then we introduce a way to calculate the mixture is by proportion of 1 component plus the proportion multiplied the other components. Okay, right, then we talk about heating a room. If we want to heat a room, we supply warm air to the room to compensate heat loss in the room. So in the winter scenario, we have heat loss through the windows, through the infiltration, through the roof, through external walls, and so on and so forth. Altogether, there's heat loss to outside. If we do not provide heat in the room temperature will drop. So therefore, we supply warm air into the room, allow the temperature to drop to room temperature. So therefore, the warm air lost temperature to the room temperature. So therefore, it provides heat to the room. Same, the cooling. In summer scenario, we have heat gain through solar penetration, through the heat airflow coming into the room through infiltration, and we also have human bodies, instruments, and other office equipment, and so on and so forth, all generate heat. If we do not remove that heat, the temperature in the room will raise, and then we'll start to feel discomfort. To avoid the heat temperature raise, the heat accumulates. We supply cool air and lower than the room temperature. So therefore, air go into the room, raise to the room temperature. That is the process of absorb heat in the room. So when we supply warm air into the room, we provide sensible heat to compensate for heat loss in the room to maintain a comfortable temperature in winter. Similarly, in summer, we supply lower temperature air into the room, allow it to raise, so therefore the coming in air absorbs heat to maintain the room, to avoid the room temperature raise. This is we remove sensible heat. Now, in both scenarios, winter and the summer, we have people. People always release moisture. So therefore, in both seasons, we supply drier air. So the drier air contains less moisture content, go into the room, it's able to absorb the moisture evaporated from people. So therefore, the humidity in the room will remain stable. And that applies to summer as well as winter. So these we call engineering solution or the applications. Okay, so these are what we have done so far. We can summarize on this by this slide. Now let's look individually. We look at room air as a mixture of dry air and vapor. So therefore, sensible heat. And we look at heat exchanger, and we look at the latent heat. So the sensible heat for the dry air and the latent heat is for the vapor. Okay, so now let's see how do we calculate sensible heat. So we have QS, let me write this QS and equals specific heat of the material multiply the mass flow rate and multiply temperature raise, temperature change. So this now is not energy but heat, is power. So no longer kilojoule but kilowatt. And here is no longer kilogram but kilogram per second. Okay, so that's sensible heat. If you apply the air specific heat and this air flow rate, this air temperature raise, this will be air sensible heat gain. If delta T is negative, this will be air sensible heat lost. So sensible heat is a heat stored in a media. It can be water, can be air. If it's room air, then it has two components, dry air and vapor. So we saw already electricity goes into the water and the water becomes hot. So there's a temperature raise, so there's energy stored in the water, and that energy is called sensible heat. And it comes from electricity. Okay, and if the temperature doesn't change, for example, when we boil the water temperature reached 100 degrees, it doesn't go further, so the temperature doesn't change, so the sensible heat doesn't change. However, the electricity goes into the water, becomes latent heat. Latent heat means it turns water to vapor. Okay, so the turning water into vapor is latent heat. And then if we move away from the water in the kettle, we look at the surrounding room air. If the kettle lost the vapor, then room air will gain the vapor. So therefore, water lost energy, the air gain heat, gain energy, but the energy gain is called latent heat. And the latent heat is calculated as QL, latent heat, is the heat of evaporation multiplied mass flow rate. Mass flow rate. Okay, mass flow rate. Here, we need to be careful. This is how much mass a second lost. Okay, and later on we will see another formula which is mass flow rate is for air, it's not water. Okay, here. So this, be careful. Okay, this mass dot is the evaporation rate, is how much kilogram water turn into vapor per second. All right, and what we see later is QL equals HE, mass flow rate, and moisture content change. In that formula, this will be air flow rate. All right, so don't be confused. Right, so the heat exchange between two media through a heat exchanger, a coil, the airflow gain will be water flow loss. If airflow loss will be the water flow gain. So there's a 100% transfer from one media to the other. And that is an ideal scenario. In reality, there is always some loss to surroundings. Okay, so therefore there's always some kind of waste. So after all, what we mentioned, the concept is sensible heat, and the other is latent. That is air gain vapor. It's latent heat. So these are the most important concepts we have been dealing with. Now let's look at the psychrometric chart. Psychrometric chart is a very useful tool we are using in air conditioning design. And so let's see room temperature, how we can present room temperature on room condition in the psychrometric chart. Let's say we have a room air measured by a sling thermometer. We have dry bulb 22C dry bulb and 16C wet bulb. So therefore, from 22 is this vertical line, 22 here, and then 16. These figures are wet bulb temperature. So we have a cross point here. This is the state of room air. Okay, so the state can be presented as one dot on psychrometric chart. And then from here, we can read all other psychrometric properties. Right, the first one is if we draw a horizontal line to the right, we read the moisture content. So here we can see the moisture content is 0.009 kilogram vapor per kilogram air. And we use G to present this variable moisture content. And then if we draw the parallel line to the curves, we can read this is saturation. It's between 60 and 50. So we just estimate saturation is 55%. And this figure 55 can be also regarded as relative humidity. Now let's move on. If we draw a parallel line to this specific volume, and we find this line is very close to 0.85 cubic meter per kilogram, and the next one here, this line here, vaguely, but this is 0.84. So you can say this is very close to 0.85 rather than 0.84. So we assume is 0.848 cubic meter per kilogram. This is a specific volume of this room air. Means if you have 0.84 cubic meter air, it will have a weight of 1 kilogram, right? So it's a reverse density, okay? Right, now let's carry on further. We draw a line from here to there, let this cross this point, and that point is about 45 kilojoule per kilogram. What's this? This is a specific enthalpy, right? So therefore, specific enthalpy HA equals 0.0. Enthalpy is 45 kilojoule per kilogram. Okay, let's see the last but not the least. So from this point, okay, let me use the laser pointer. From this state of room air, if we cool it, reduce the temperature, previously we couldn't see the vapor, and then to this point, and we start to see the mist. Or if the room has a surface at this point, 12.5, we start to see the surface dew start to appear. So this is called dew point, 12.5. So altogether we have this 1, 2, 3, 4, 5, 6, 7, all 7 psychrometric properties for the room air. So the state of air here at this point represents the state of air. It can be represented by at least 2 psychrometric properties, and others can be all found out from this psychrometric chart. Among all those 7 variables, the enthalpy can be a hard variable to understand. So therefore, let's look at this exercise. The psychrometric chart shows the enthalpy of the state of air if the air changes from one state to another, and then the enthalpy changes. So from the enthalpy change, we can find how much energy gained or lost from the air. So this is how we look at this one. So here, we use the red one. This is a mass flow rate. This is a mass flow rate. Mass flow rate is 1. This is enthalpy change. If enthalpy change is a positive gain enthalpy, this will be the heat gain. If enthalpy is negative, it's lost, there will be energy lost. And the enthalpy, you can see, is 1 kilogram energy contained in the air. And it has 2 components. One is sensible. You can see it's associated with temperature change. And this 1.01 is dry air. 1.89 G is the moisture content. So this becomes the moisture. The moisture itself, if temperature change, it also store energy. The next one is, remember this, heat of evaporation multiply moisture content. So this will be latent heat. Okay, this will be latent heat. So here are the questions. How much water has been evaporated off from a kettle over 2 minutes boiling? So we know how to calculate this one, explain this already, right? And then we also demonstrate how you calculate the moisture into the room air and change the moisture content in the room air. Okay, because room air moisture content is calculated kilogram vapor per kilogram dry air, kilogram air. So therefore, you need to consider the total vapor in a big room and how much weight of the room air. So therefore, you use the moisture weight divided by room air weight. So you get the moisture content for the room air. Okay. Now let's see the application of the sensible heat. So Q equal mass flow rate multiplied specific heat multiplied temperature change. This can apply to air and it can be also applied to water. Now let's see this example. Here we focus as number 3, this heat exchanger. It allows airflow to go in here and the water flow going inside the pipes. Okay, so therefore you can see this is a heat exchanger. And then if, let's say, the boiler provide hot water come in here, and then coming out here. And the water, hot water is to heat up the air going from here to there. Okay, so we look at this one, how we apply this. Okay, so here this T2 is after heating if we focus the air, and then T1 is before heating, and then the CP will be specific of air, and M will be air mass flow rate, and this will be heat gain by the air. So if we do the work to the air, the temperature raise. If the temperature drop, so heat's being taken away. Okay, so that's the first application. Now let's move on to a big map, this big map. Okay, big map, if we for this dark blue, this airflow, dark flow, so it starts from the outdoor coming through this preheater, we call this preheater, and then the air after heating will join together by the return air from room and going into the second coil. This is a cooling coil, and we need to imagine 2 scenarios. If now is summer, so this heater will be turned off. So therefore, the outdoor air mixed with room air going through this cooling coil, and inside cooling coil, there's a chilled water. So therefore, chilled water absorbs heat here, and then this temperature will be lower, and because the surface will be very low and lower than dew point, right? It can be lower than dew point. So therefore, you can see not only temperature drops, but also moisture being turned into dew, become condensate. So therefore, at its coil, air lost both sensible heat and the latent heat. And then go over here, there's a reheater. Sometimes we switch it on, even in summer, but in winter, definitely this is on. Then air going another device which sprays vapor. So this is a humidifier. And then driven by the fan and pop through this ductworks into the room. Remember, in summer, the supply air go in, will have a lower temperature and then absorb heat here, raise the room temperature and leave. And similarly, in another room, going into in a lower temperature, absorbs heat, raise temperature, the room temperature, comfortable temperature, and then leave. Now, also, the supply air will have drier, lower humidity content, so therefore they can absorb human moisture and then move. So this is a summer scenario. In winter scenario, the air coming heated by preheater, and then this cooling coil is off, and reheater heat again, and the air going through this fan, driven by the fan and coming into the room with higher temperature, so therefore it can drop and release heat into the room to compensate the heat loss to the outdoor environment. And similarly to another room coming in at warmer temperature, so therefore drop to the room temperature to compensate heat loss to the outdoor. So you can see this is the big map for the air circle, airflow. So the first circle is airflow. Then heat flow marked by red. So you can see heat always come from the boiler's room. So boiler generate hot water and circulate in this preheater heating coil. And then this is another set going to reheater. So this is hot water flow. Now chilled water is produced in chilled plant. And you can see this going into the cooling coil in number 7. And 8 is a valve to allow this bypass all going into the cooling coil in summer. Right? And then this circle, we don't see complete picture. It is a refrigerant. Refrigerant take heat away from evaporator and dump the heat at a condenser to the cooling water. Cooling water, we don't see this, but with a bigger map, you will see the pipes linked to the condenser take the heat away from the condenser, deliver the heat by this cooling water, dump the heat into atmosphere at cooling tower. And the cooling tower and this air handling units are the two subjects in our lab work. So therefore we do 2 tests, one for air handling units, the other for cooling tower, to find out, to prove or disprove 2 hypotheses. One for air handling units, the other for cooling tower. Okay, we will explain this more when we explain the lab work. So that is how in engineering we realize the state change for the air by heating, by cooling, humidification, dehumidification. Right, now in this exercise, we do some calculation to show how the sensible heat, Q equals Cp multiplied flow rate multiplied temperature change, can be applied to air, can be also applied to the water. Okay, here it says that outdoor air temperature has -5 and a saturate. So it has a flow rate of 0.5 kilogram per second coming into the air handling units through the heater. Okay, and now the air raised temperature from -5 to 15 degree dry bulb. So you can see the TA1 equals -5 C, and TA2 is 15 C. Okay, so you can see the temperature increase, and the flow rate is 0.5. So we have the temperature delta T equals 20, and the mass flow rate is 0.5 kilogram, and the CP air is 1.02 kilogram. And then we can calculate how much heat is gained by the air. Okay, so now we apply into this. Okay, we add all this subscripts to represent this is air. And similarly, we put W represent this is for water. Now let's see what questions are. So here it asks that to calculate heat input from the heater. This can be the heat gain by the air or the heat loss from the water. Let's start from this one, is air. So we now right here is surface heat of air is 1.02 kilojoule per kilogram. Multiply mass flow rate is 1.5 kilogram per second, and the temperature is 20 K. So there's a K here, kilogram per kilogram, kilojoule per kilogram per K. So K cancelled, kilogram cancelled. So it'd be around kilojoule per second. So therefore you have a heat is 1.02 multiplied 0.5 multiplied 20. So 20 by this by 0.5 will be 10. 10. So therefore it's very easy to calculate. It's 10.2 kilowatt. Is that right? 0.2, yes. So it's a 10.2 kilowatt heat gained by the water. Now the same if water gained by the air gain will be the heat lost. So therefore he asks if the water drops 15 degrees in temperature, so calculate flow rate of water. So if we know this is 15 C or K lost, there have been minus, so this is to be calculated. We know this is 4.18 kilojoule per kilogram per K, and then we know the heat, that equals minus. All right, so what we can calculate here is that this one we have minus 1.2 kilowatt equals CP 4.18 kilojoule kilogram K, and here mass flow rate is to be calculated, W, and then 15 K, okay, K cancelled, and the kilowatt is kilojoule second. All right, so kilojoule cancel, so you have kilogram second. So therefore, what mass flow rate W will be? This is a minus, all right? As I said, minus here, minus. So the minus, these two minus cancel each other. So you have 10.5 divided by 4.1 multiply 15. Unit will be kilogram per second. Okay, you work it out. 10.2 divided by 4.18 divided again by 15. That will be the water flow rate. Okay, so what we see here is sensible heat gained by one media in contact with another in the heat exchange will be the heat loss of the other flow. Here, the air gain will be the water lost, because these two flows actually meet each other at the heating coil. So this, if you think about this device in our laboratory, the heater will be charged by electricity, and we can measure the current and the voltage. So we know how much power input, and we can calculate the heat input by the heating coil, electric heating coil. and we can estimate the heat raised by the air. Okay, so that is application, one of the many applications. Earlier we said that enthalpy is a new concept. It's probably the hardest one to grasp. Now let's have another look. So as we said already, the enthalpy is some kind of energy contained in a piece of air. So it is two components. One is the sensible, the other is vapor. Okay, so if H represents enthalpy, now U will be the sensible energy. Now the P will be the pressure, vapor pressure, basically is the moisture content. Okay, moisture content. So here we see, now we are familiar already with this enthalpy, the specific heat of water. Now dry air has a 1.01, so it's much smaller than the specific heat of water. Now vapor is a state between air and the liquid, so therefore it has some specific heat between the two values. So it's nearly 2, right? And unit is a kilojoule per kilogram per K, right? Per kilogram per K. So now let's see what is the specific heat of mixture air. So it is specific heat of dry air and the specific heat of vapor. So you can see this is air, this will be moisture. Remember, multiply G, so you turn the gram of air into gram of moisture. So you can see the G is a very small number, okay, 0.009. So therefore, actually, the sensible heat, the specific heat contribution from the moisture is very, very small. It's negligible. Okay, this part is negligible. What most contribute is latent heat. Let's see this. So this will be latent heat. Okay, so remember the G, what we did in the schematic chart, right, is 0.009. So very small, but multiply 2,500, that becomes significant. So latent heat is really a big, significant contribution from the moisture. And the sensible contribution to the air is minimum. And so therefore, basically, the sensible primarily by the air and latent primarily from the vapor. So altogether contribute the enthalpy, which is the total energy contained in the mixture. All right, so it's sensible plus latent. Sensible plus latent. Okay. We have seen the heating coil. Let's look at the cooling coil. And here is an example, this question. An outdoor design condition in summer, the air condition has two variables. One is dry bulb, the other is wet bulb or saturation. Here is 28 Celsius dry bulb and a 60% saturation. A system uses borehole water to cool the fresh air back to the air. 28 Celsius dry bulb, 60% saturation in its air handling units. The cooling coil maintains an average surface temperature 12 degrees. So this what we call is apparatus dew point, 12 degrees. All right. So the contact factor is 0.8. And the question is to calculate the off-coil temperature. Means if this outdoor air going over this cooling coil, which maintains at 12 degrees, and what temperature it will be after in contact with the cooling coil, right? And then also not only temperature drop, but also there's a loss of moisture, and how much we need to calculate. And this actually is slightly more difficult than previous one because it involves sensible heat and also latent heat. Not only temperature drop, but also moisture content. lost. Now, device, that's for illustration. We have cut off the skin of one section of duct work. And we can see this is solid line represent copper pipes, and they wear together in parallel. So therefore, we have 4 streams going over, and they wear together with plates. These plates are aluminum, so therefore they are all good thermal conductors. So we can see these are all maintaining the same temperature, 12 degrees, and the air going over at 28 degrees, surely it will drop temperature. But at the same time, it may also lose moisture because the 12 degree may well below the dew point of this outdoor air status. We will draw this on psychrometric chart to check it out. Anyhow, let's work out contact factor first. Contact factor applies for the temperature. So this is temperature. One is after and before, all right? So here we can see the apparatus dew point is 12 degrees, okay? And then from psychrometric chart, we don't need a psychrometric chart at the moment, but anyhow, let's look this formula. TA is after. In this case, TA is before treatment, and the TB is after. So this is before treatment, and this is the device temperature. So here you have 28 before, after. That is what we need to calculate. Now, the lower one is before 28 and going over a 12 degree, the very cold surface. And that is the definition of contact factor. And that equals 0.8. So very easily, we can calculate the air out here will be 15.2. Okay, now let's look at this one contact factor, right? This top is temperature difference between, because of this exchange, the temperature change, okay? And the lower one is the temperature difference between before treatment and the device temperature, okay? So you can imagine if a contact factor is 1, that means these two equal each other. That means the TB will be TC. So the T temperature out will be the temperature of the device, 12 degrees at lowest. So that means this is the ideal, the best the coil. Coil allows the air after the treatment reach the temperature of the device itself. That is ideal, but doesn't happen very often in reality. Or we can say it never happens in reality. But if there's no contact, so the temperature doesn't change, this temperature coming at 28 degrees, out at 28 degrees, so therefore 0, so there's 0 contact. So this coil doesn't affect at all the airflow. Okay, so that is how we calculate temperature drop. Now, we plot this 28 saturation, we can find out the moisture content before the treatment, right? Now, it's 0.0144 kilogram vapor per kilogram dry air. How do we know that? Here, this is 28 temperature, and this is 60%. Okay, so this dot represents outdoor state, the state of outdoor air. So drawing a horizontal line, we can find the outdoor air moisture content is 0.0144. Next one is 0.015. So this will be 0.0144. Okay, so that is the before. We have this one is outdoor air. Now, how do we draw the 12 degree? The device we call the apparatus dew point. Sorry, it's not APD, it's ADP, apparatus dew point. Okay, here is 12 degrees at the saturate. Okay, now remember, what is the dew point of this temperature? Dew point is here. We draw a horizontal line to meet 100% saturation. So you can see for this amount of moisture content in the air at 28 degrees is only 60% saturated. And if we reduce room temperature, it becomes 80% saturation. If we reduce further to 20 degrees, it's almost 100% saturated. So you can see if in the room there's a surface has a temperature lower than, let's say, lower than 19 degrees, and we'll surely see the surface accumulate the joules. Actually, the condensation happens. Now imagine if in this 28 degrees, 60% saturated, you take a can of beer out of fridge, you immediately see the surface covered by the joules because surface is much lower than 19 degrees, right? Anything lower than 19 degrees, you will see the condensation. So the surface at 12 degrees surely will covered by condensation, right? So therefore, if we draw a line joined together by the O and the ADP, this line meet another vertical line represent the 15.5, which is off coil. Remember the TA2, and the meeting point, this point represent the state of off coil temperature, off coil air. So we calculate from contact factor, the temperature is 15.5 dry bulb, and then the moisture content will be here. So the moisture content will be 0.0102, okay, 0102 here. Now 0.01 kilogram vapor per kilogram dry air. This is the moisture content. And if you like, you can read this. Y bulb temperature is 14.5 Celsius dry bulb, right? So this, you take the air to the cool surface, and out air will be on this line. If the contact factor is very, very large, very close to 1, this off coil will close to this point. If the contact factor is very small, the off coil temperature will be close to the O. Okay, if the contact factor is close to 1, it's close to the ADP. Okay, but now 0.8 at 0.8 is 20% close to ADP, 80% away from the outdoor. So this is off coil state for off coil air, and the moisture content is GA2. So remember, the second question is estimate the moisture lost at the cooling coil, right? So therefore, how do we do this? We bring back this device, so the air going here has more moisture, GO, and out the GA2, right? Less moisture content. So now this is a drop moisture content. Okay, drop. So the drop delta G is GO minus GA2. So previously it is 0.0145 minus 0.01. So that will be per kilogram air, how much lost. Okay, now if air flow rate is 2 kilograms per second going over the coil, 1 kilogram will lost that much, and 2 kilograms per second is just delta G multiply 2 kilograms per second. That will be the moisture lost. So if we calculate vapor lost, or vapor turn into condensation, is mass flow rate of air multiply the moisture content change. So the 2 kilogram per second multiply the difference, and we obtain the 0.09 kilogram vapor condensate per second. So every second we gain about 9 gram condensation water. Okay? So you can imagine there will be some kind of water drip here, right? 9 gram every second. 9 gram every second. So a few drops every second. Okay? Now, let's see how much heat being taken away from the air. We know that from here, temperature drop from 28 to 15.5. The temperature drop of air means the air lost sensible heat. And we just calculated moisture lost from O to the GA2, GO to GA2. So therefore, the air also lost the moisture. So there's a latent heat lost. Now, how much we can calculate? Use the formula we learned before. So how much latent heat lost? So overall, the flow rate, we calculate already. So this is mass flow rate. What we calculated earlier is mass flow rate multiplied delta G. Right? That is how much moisture lost. Now, if we multiply by the heat of evaporation, we can turn that amount into heat. So we calculate 0.009 kilogram per second, the generation of condensation, and multiply by the heat of evaporation, 2,500, and we have 22.05 kilowatt latent heat, because this heat is lost in form of lost moisture. Or you can say, from cooling coil point of view, is the coil has taken away the moisture from the air, right? So how much latent heat? 22.05 kilowatt. Latent heat being taken away, or equivalent to that amount of heat of vapor being taken away. Right, so how much sensible heat? And we know this already. Sensible heat QS equals mass flow rate multiplied specific heat of air multiplied temperature change of air. So therefore, m dot multiplied Cp air multiplied TO minus TA2. So air flow rate is 2.0 kilogram per second multiplied the specific heat of air. Specific heat of air is 1.02 kilojoule per kilogram per K. Multiply temperature drop from 28 to 15.2 kilogram K. So K cancelled, and the kilogram cancelled. So you have kilojoule per second. So it's a kilowatt. So therefore, the product is 26.11 kilowatt. So that is sensible heat, right? Okay, so we use these two formulae to calculate sensible heat and sensible heat. We put them together. So how much energy lost? How much energy lost from outdoor air to off coil? Previously, before going in, it has so much energy and lost so much, right? So therefore, altogether is these two plus together. So 22 latent plus 26 sensible, we have 48.2 kilowatt. That is adding these two together. Now, let's see how the psychrometric chart can help me help us to do the calculation for the total energy lost, heat lost. Okay, so if we draw the diagonal lines to cross this off coil, the other cross the O, and this reading is 65 kilojoule per kilogram, and after coil, and it's only 41 kilojoule per kilogram, right? So therefore, the total heat lost will be mass flow rate multiply enthalpy change. And the mass flow rate is 2.0 kilogram per second. Then enthalpy change from 65 to 41. Unit is kilojoule per kilogram. Kilogram cancel. Kilojoule per second is kilowatt. So we got a 48.0 kilowatt. So compare with these two, they are very close. So you can see use psychrometric chart, enthalpy really means the energy change of the air. Okay, so use this example, we can understand better the two components, sensible heat and latent heat. And also these two components make up the enthalpy. Make it up enthalpy. And also from here, we know the energy lost from the air will be gained by the borehole water. Okay? Right, now let's discuss about this phenomenon because this is very new. And we covered the sensible heat, latent heat. We also covered the enthalpy. Now let's look closer. The air for loss of both sensible heat as its lost temperature. So TAO, which is 28 degrees, going over here becomes 14.2. So therefore, there is a sensible heat lost, and it can be seen as temperature drop. Now also, there is a latent heat lost, can be seen as moisture lost. So condensate are gathered at the bottom, right? So because of the chilled surface, right? So from the sensible heat lost, there's a temperature drop. We use this formula to bring this together. Okay, sensible heat, and the temperature drop to link these two together. Now for the latent heat, this is the surface of a cane, and in the room we see the dew happens. So that means the room air lost latent heat because it's in contact with low temperature surface. The surface is lower than the dew point of a room, and then inevitably it lost moisture. And the latent heat is associated with the moisture content change, multiply the mass flow rate, and multiply the heat of evaporation. So we have these two formulae linked together: temperature drop, moisture change with specific heat, and heat of evaporation, and then the two sensible heat and the latent heat. So the total energy lost from airflow has two components, one sensible, the other latent, and can be calculated by the flow rate multiply enthalpy change. So what is enthalpy? Enthalpy is the energy contained in the